Hello and welcome to Woven Chemistry. I'm Jean Weaver, and in this video we're going to focus on standardization of a sodium hydroxide solution. Specifically, we're going to focus on error analysis. This is definitely the higher level thinking, the thinking that will get you that 5 on an AP exam or maybe an A in a Gen Chem class. If you didn't watch parts 1 and 2, I recommend that you do that, especially part 2, so that you thoroughly understand a standardization procedure. All right, let's get started. So here's the first question of 6. So here's the question. When standardizing a sodium hydroxide solution, you accidentally used KHP that had not been stored in a desiccator, nor had it been dried in an oven. What impact, if any, will this have on the concentration that you calculate for the sodium hydroxide solution? Be sure to explain your answer. And don't just say that your results will be skewed or that they'll be off. You need to say, if there will be an effect, if that final concentration will be overestimated or underestimated. Okay, pause the video, think this through, jot down your answers, take a few minutes because it does take a few minutes to figure it out. All right, let's think this through. So ideally, we're going to use dry KHP, okay? And here's our equation. The measurements that we need are the mass of that KHP and the volume of the sodium hydroxide. We'll use that mass to get moles of KHP. We'll use that to get moles of sodium hydroxide. We'll take the volume and the moles together and we'll get our final concentration. So that's what's supposed to happen. Now let's throw this error in, okay? And the KHP now is damp. All right, so that means that this 0.3072, that's not right. We actually have less than that. But we're going to use the 0.3072 because we don't really know any better. So this number here is too high. Okay, 0.3072 is too high. So when we calculate the number of moles, we're using a too high number to start. So that means the moles we calculate will be too high. Okay, it'll also be too high up here. So now when we calculate using that 1-to-1 reaction ratio, the moles of sodium hydroxide, that's going to be too high. Now let's think about how we calculate the molarity. Molarity is moles per liter, so those moles are going to be too high, and if the numerator is too high, that means that the answer is too high. So we're going to end up with a value that is too high. Okay, our final concentration is going to be too high. So in the end, there will be more KHP used in the calculations than what you actually used in the procedure. This is going to cause you to overestimate the number of moles of sodium hydroxide present, and because molarity is moles per liter, the final concentration of NaOH will be overestimated as well. Okay, so it's not only important to understand this, it's also important to be able to write this down. So really, I encourage you, take the time and actually write down your answer and see if you can get an answer that's nice and crisp and clean. Okay, moving on to the next question. You're adding sodium hydroxide to the KHP solution with a burette, and you notice that there's been no sign of pink from the phenolphthalein, which makes you realize that you forgot to add it. So you put a couple of drops of phenolphthalein in the flask and the solution immediately becomes pink. Even when you swirl it, that pink color remains. Can you safely use the data from this trial to calculate the concentration of sodium hydroxide solution? All right, let's kind of walk through exactly what happened here. So what we're supposed to do is add the drops of sodium hydroxide to this KHP phenolphthalein solution drop by drop. Drop by drop. Okay, so here's another one, and here's another one, and let's add one more. And this is the one that causes the phenolphthalein to turn pink. This is what's supposed to happen. So you stop. But remember, in this mistake, we didn't add the phenolphthalein. So that's not there. We don't know any better, so we keep adding. We add a little bit more, we add a little more. And then we realize, oh, shucks, I forgot to add that phenolphthalein. You put it in right away and it automatically turns pink. So this final volume that's supposed to be 20.77, it really turns out to be something larger, let's say 22.77. Now let's think about that effect on our results. Here's our equation. There's our mass, there's our volume, okay? But that volume is we're actually using 17.7, which is too high. Okay, we should be using 15.5, but we're using a number that's too high. So let's think that through. The mass will get converted to moles of KHP, which will get converted to moles of NaOH. When we calculate the concentration, the denominator is going to be too high. Now, is it going to be exactly 17.7 milliliters? Probably not, but the point is it's going to be too big. If your denominator is too big, then the overall answer is going to be too low. So that means that we will underestimate the concentration of the sodium hydroxide. So in the end, this trial should be discarded. It's essential to add precisely the correct amount of sodium hydroxide so that moles of KHP present equals moles of sodium hydroxide added. By adding that phenolphthalein too late, it's very likely that you added too much sodium hydroxide, and the data from the trial, and thus the data from this trial will result in an underestimation of the concentration. Question 3. Okay, to account for any minor error that might happen, you repeat the standardization process 3 times and plan to average the final concentrations. You're very careful to do everything the exact same way between the trials, but you weren't consistent with the amount of water used to dissolve the KHP. Is this a problem? Okay, so let's think it through. Again, we're going to have the sodium hydroxide in this flask, and we're going to drain it down drop by drop into this flask that contains KHP and phenolphthalein. And from this, we're going to have a couple of measurements, the mass of the KHP and the volume of sodium hydroxide. So we'll take that, and so what we want to do here is focus on these measurements and the calculations and see if the volume of water that we use for the KHP factors in anywhere at all. So here we go. That mass gets converted to moles, and the moles of KHP gets converted to moles of sodium hydroxide, and then we'll use the volume and the moles to get the overall concentration of the sodium hydroxide. That's what should happen ideally. When we look at this, we haven't taken into consideration at all the volume of water that we would use. So what that means is it doesn't matter at all. Using different volumes of water to dissolve the KHP each trial doesn't matter. As long as we use enough water that the KHP properly dissolves and that mixing and contact between KHP and sodium hydroxide isn't compromised, the amount of water doesn't matter and your results should be just fine. Question 4. When performing the calculations, you thought that the KHP was a diprotic acid, not a monoprotic acid. What effect, if any, will this have on your calculations of the sodium hydroxide concentration? Explain. Okay, so what's going to happen is we're going to have a 1:2 reaction ratio between the KHP and the sodium hydroxide. How does that play out in the calculations? Well, here are our measurements. Those shouldn't change, and the mass will get converted to moles of KHP. Those moles will get converted to sodium hydroxide, moles of sodium hydroxide. But because we think it's a 1:2 reaction ratio, we're going to double the moles, and that's going to be an error. The moles of sodium hydroxide will be too big. Okay, let's think that through. When we calculate molarity, our numerator is too big, which means our final answer will be too big, and we will get an overestimation of the sodium hydroxide concentration. Question 5. So when setting up the titration, you rinse the burette with water. What effect, if any, will this have on your calculated concentration of sodium hydroxide? All right, so let's take a look at the situation. Here's our equation, and here are the proper measurements and the proper calculations if we had rinsed it with sodium hydroxide. Now, as the question says, we didn't. We rinsed it with water. Okay, so we'll start out with 5.07 milliliters. But when we drain it, when we drop this sodium hydroxide down into the flask containing KHP, these initial drops won't contain any sodium hydroxide, so they won't do anything. So we're going to have to drop this down a little bit further. Let's say we drop it to 22.7, when it should have been 20.77. So that means that our 15.7 milliliters that we should have, we're really going to have a bigger number. This is going to be too high. Well, how does that factor through in the calculations? It comes in with when we calculate the molarity. Our denominator will be too big, which means our final answer will be too small. Okay, so our final answer will be an underestimation of that concentration. So rinsing with water will dilute the sodium hydroxide solution, causing you to use a greater volume of sodium hydroxide than you should to neutralize the KHP. And since molarity is moles divided by volume, the molarity of the base will be underestimated. All right, last question. So let's say you weighed the KHP out very carefully on an analytical balance, but you lost a few grains when transferring it to the volumetric flask. What effect, if any, will this have on your calculated concentration of sodium hydroxide? Okay, here we go. Here's the scenario. Okay, we weighed it out and we needed 0.3072 grams. We weighed that out precisely, but when we're transferring it to the flask, we lost some along the way. Okay, so that means when we're doing our calculations, this 0.3072 is too big. So that means that our moles are going to be too big, and that means our moles of sodium hydroxide are going to be too big. So when we combine that together, moles is in the numerator, that means our concentration will be too high. Now that's one way to think about it. Another way you might think about it is this. Okay, since we have less KHP in the flask, that means that the volume that we need, okay, what we should have done, if we had all of it in, we would have drained it down to 20.7. But since there's less KHP here, we don't need to drain it quite as far. Let's say we drop it to 19.77. All right, so let's think of it this way. That means that our volume that we use, we're going to use 14.7. Well, that's too low. We really should be using 15.7 in our calculations. Well, how does that error follow along? Okay, so molarity down here, we should be using 15.7. We're using 14.7. That's too low. Okay, so if the denominator is too low, that means the final answer is too high. That's the same answer we got before. And so in the end, we come to the same conclusion just by thinking it through differently. So my point here is there's a number of ways to come at this final answer, but the process and the thinking is all the same, and fortunately, the final answer is all the same. So in the end, there will be less KHP used in the titration than what you use in the calculations. This will cause you to overestimate the number of moles of NaOH present, and because molarity is moles per liter, that final concentration of NaOH will be overestimated as well. Okay, so what we've done in this three-part series is in part one, we took what it means to standardize a solution and why it needs to be done. Then we took the thinking up a little bit, and part two was about understanding a standardization procedure rather than remembering it. And then this third part was really the highest level thinking, evaluating procedural errors and explaining their impact on the calculated concentration. I really hope that you sense after watching one or hopefully all three of these videos that your understanding and your thinking has really expanded and developed. And I just want to reflect on just a little bit here. I always think it's important to think about the macroscopic, microscopic, and symbols and calculations and weave all of those together because they help you figure out the answers. Thinking about the microscopic and the microscopic flaws allowed us to realize the errors that were involved in what the macroscopic balance was telling us, and that allowed us then to think through the accuracy of our results. So as always, thank you so much for joining me, and I hope to see you again soon.